All right, let's talk infrared. First of all, just a little review here about what spectroscopy actually is. Mass spectrometry is not spectroscopy. Spectroscopy is a system of measurement by absorption of electromagnetic radiation. So here's the electromagnetic spectrum. If your sample absorbs any kind of electromagnetic radiation around here, then it's spectroscopy. Mass spectrometry, we're just measuring metry. We're just measuring masses that come through a detector. There is no electromagnetic radiation being absorbed or transmitted. So visible spectroscopy, stuff that you did back in general chemistry, with Beer's law, you can figure out the concentration of a solution based on how much light is absorbed through it. We're going to be interested in infrared spectroscopy and ultraviolet later on in the next chapter, but infrared spectroscopy is interesting to us because infrared spectroscopy measures the amount of infrared radiation absorbed by samples, and it shows the types of bonds and functional groups present in a substance, in an organic molecule. Notice we say Fourier transform, FTIR. That same Fourier transform process is used in NMR. We talked about it a little bit there. That's where multiple frequencies are shown through the sample all at once with just one detector, and it sorts out what frequencies came through and what were absorbed all at the same time. It used to be, in the olden days, there would be something where there would just be one wavelength, and then try another wavelength and another and another and another, and you'd step through all those wavelengths and measure how much was absorbed, much like you would with a ch12 visible spectrometer. But with the advent of FT, it gives a what's called a broadband stream of radiation that has all of these wavelengths all at once, and just all at once it records what came through and what didn't. So that allows for multiple scans to be set up. When we use our IR instrument, it takes 16 scans and averages them all together to get a little better signal. This is the insides of an IR spectrometer. There's a light source. I believe it's right here. Guess I'm not sure which end is which, but the key is it uses laser light source, for instance, and in this case the sample is on a clear piece of film, and the IR energy shines through there, and the detector sees which frequencies of light had been absorbed by it. Classically, this was the only way to do IR. If you had a liquid sample, you had to apply it to some a couple of salt plates or something like that you would sit in there, and the sample would shine through it. Now, sort of the state of the art in IR is called ATR, attenuated total response. This part of it right here is the ATR unit, and you'll recognize this from the instrument that we have. The sample just gets, just put a couple drops on the sample right there. If it's a solid, put a little scoop on right there, and this arm will press it down to make sure it's in good contact. But what happens in ATR is the light sample actually comes up and bounces just on the underside of your sample and bounces right back, and it actually goes into your sample a little bit. Some things are absorbed and then some are reflected back, and you get the same information. It's just so much faster and cleaner and more convenient than having to prepare salt plates and clean all that stuff up every time. So just works a lot better, especially for a teaching situation where there's a whole bunch of us that need to make measurements all at once. So the reason infrared radiation gets absorbed by organic molecules is because